is kinetic molecular theory. It tells us that gases are made up of particles, usually molecules. We'll call them molecules here, but they also include monoatomic gases like helium or xenon, those noble gases. But they'll call them molecules anyway. And these molecules are separated by a good distance, more than the size of the molecule. So what we do with that means that we consider the volume of each molecule to be 0, even though that's obviously not true. Everything takes up some space, even if it's very, very tiny. But for this theory, we're going to assume it's pretty much 0. These gas particles are in continuous, random, rapid motion. They're moving around really fast, random directions, never stopping. So that is the second tenet, or the second idea represented in kinetic molecular theory. The one that we're going to talk about the most here is the average kinetic energy of gas molecules is determined by temperature, only by temperature. So there are no other variables that determine the average kinetic energy of gas molecules. You might think, oh, that's weird, because we learned that kinetic energy is equal to 1/2 mass times velocity. And we're going to learn a lot more about this equation today. But the key thing in this sentence is anyway, because it's only dependent on temperature, all gas molecules at the same temperature. Doesn't matter how big they are. Doesn't matter how fast they are. All gas molecules at the same temperature have the same average kinetic energy. All right, so remember that. When molecules collide with each other, this is the last step. When molecules collide with each other or the walls, they don't lose any energy. That's not true, but that's another assumption in the kinetic molecular theory. We call these perfectly elastic collisions. So perfectly elastic means no energy is lost. All right. So kinetic molecular theory, so far it sounds like it makes a lot of assumptions, but it is consistent with the gas laws we have learned. So Charles' law, Boyle's law, Avogadro's law, the ideal gas law, it's consistent with those. At the molecular level, pressure, we'll talk about pressure first, relates to the number of collisions between gas molecules and the inside of the container. So the more collisions between gas molecules, then between gas molecules and the wall, the higher the pressure. So each collision involves a force. That force pushes on the inside of the wall, and we learned that pressure is equal to force over area. So those collisions have a force, which means they create pressure. The more collisions there are, and the more energetic the collisions are on average, so the higher the kinetic energy of those molecules when they hit the wall, the greater the force and the higher the pressure. So that kind of makes sense, right? So when we change the number of molecules are moving less quickly, and they have a lower average kinetic energy than when they hit the wall less often because they are moving slower, and they hit the wall with less force because they have a lower energy. So lowering the temperature lowers the pressure. But in general, changing the temperature of a sample of gas results in changes in the other properties of the gas, in accordance with the gas laws we already discussed. So this is all still related to the gas laws, the ideal gas law in particular. So let's look at those relationships in terms of pressure. If the number of gas molecules inside the container goes up, then that means the number of molecule and wall collisions will increase. So you have more gas molecules, the likelihood of them hitting the wall is higher, and that means that at constant volume and temperature, there will be a stronger force and a higher pressure when more of these gas molecules hit the wall. So pressure and moles are directly related, which is what we see when we have our ideal gas law. An increase in P goes along with an increase in N. They're on opposite sides of the equal sign, so one goes up, the other one goes up when everything else stays the same. All right, what about pressure and temperature? So as the temperature of the gas increases, the molecules speed up. So there's more collisions when they speed up, and they have higher energy collisions because the average kinetic energy also increased at a higher temperature. This results in a higher pressure, so P and T are also direct, as you can see in the ideal gas law. So when P goes up, T goes up. When T goes up, P goes up, because they're on opposite sides of our equal sign. And if everything else stays the same, when one goes up, the other one has to go up. All right, so our last one to connect with P is volume. When the volume of the container is increased, then the gas molecule container before they hit the wall. And this means that there are fewer collisions of molecules with the wall. So if you have this size box and your molecules are moving around versus this size box, your molecules are moving around, it's going to take them longer to get over here than it took to get over here. So that's your very artistic demonstration of what I just said. So the volume of the container is increased, the gas molecules hit the wall less frequently, and we get a lower pressure. So volume goes up, pressure goes down, and that is also consistent with our gas laws, particularly Boyle's law. All right, cool. So let's get into the weeds a little bit here with kinetic energy. Gas molecules move at very high speeds, and the kinetic energy of an object is directly related to its mass and velocity, as we learned. So kinetic energy is equal to 1/2 mass velocity squared. When you have a whole bunch of gas molecules in a container, the average kinetic energy of those gas molecules is directly related to the average of the velocity, because all of those gas molecules, regardless of how fast they're moving, have the same mass if they're the same gas molecules. So we're going to look at the change in velocity. So the average kinetic energy, we label that with a line over the top, is equal to, or directly related to, the average of the square of velocity. So we have a line over the V as well. But we just learned that the average kinetic energy is also related to absolute temperature. So we can write that relationship here. Average kinetic energy is equal to 3/2 RT. Oh, sorry, up here, this Avogadro's number has to do with the fact that we're talking about average kinetic energy of 1 mole of gas particles. So that's important. That's why Avogadro's number comes in. All right, back to temperature. Average kinetic energy of 1 mole of gas molecules is directly related to temperature when you use this ideal gas constant. So note, our ideal gas constant now has a different value and different units. So I warned you that this might happen. So you have to know what units you're talking about to know which. So kinetic energy is equal to 3/2 RT. So we have the same thing in both of these. Note, kinetic energy, average kinetic energy equal to something. So if we set those two things equal to each other, we can say that the average velocity, so the average squared velocity here, is inversely related to the mass of the gas molecules, because they're both on the same side of the equation. So They are inversely related because you would move one to the other side. So, for example, you move m to the other side by dividing by it. So they're inversely related. And the average velocity is directly related to the temperature because they're on opposite sides of the equal sign. So when average velocity goes up, temperature goes up. Or more importantly, when temperature goes up, average velocity goes up. So what that means is we can find the average velocity by knowing what the temperature is. So we take a square root of our average velocity squared, and that gives us something called the root mean square, or RMS speed of a gas. It's not quite the same as the average speed, but it's close enough, so that's what we're going to use. You would see that if you plugged in some numbers that the average, if you take the average of the square and then take the square root versus if you take the square root and then the average, you get different numbers. So it is slightly different, but you don't need to worry about that for now or for the rest of the semester. So root means the average is not. So root mean square speed of a gas. This equation also shows us the relationship between root mean squared speed of the gas and their molar mass. So temperature is in here and molar mass is in here. And we got this equation by moving everything around from this equation in order to get the average velocity squared by itself. And then we square root both sides here, and we see that 3RT, we have 3RT over Avogadro's number and mass. But when we have Avogadro's number, that's a mole, that's 1 mole of gas molecules, and we have a mass for 1 mole of molecules. So when we combine those two things, a mole and a mass, we end up with the molar mass. But note, very important to note, that our new value of R that we just learned today is 8.314 joules per mole Kelvin. And because joules can be converted into kilograms times meter squared over second squared, that means that we have to use kilograms per mole when we're talking about our molar mass. Grams per mole when you are calculating for this RMS speed. So I'll show you what that looks like right now. So RMS speed, VRMS, is equal to square root of 3 RT over capital M, which is our molar mass. And if you look up the molar mass of neon, it is 20.18 grams per mole. And I just told you that you need this to be kilograms per mole. So that means we are going to divide by 1,000 because there are 1,000 grams in 1 kilogram. That'll get rid of our grams, and we'll end up with 0.02018 kilograms per mole. All right, so now we have all our numbers. 168 degrees Celsius has to be converted into Kelvin. Whenever you're talking about gases, you always need to convert to Kelvin. So 168 plus 273 is our temperature. So if we plug in everything, we're going to get square root of 3 times our new R, which is 8.314 joules per mole Kelvin times our sun here, 168 plus 273. That's got to be in parentheses. 273. It's got to be in parentheses on your calculator unless you add it together first and then plug it in. And our 0.02018 kilograms per mole. So our moles are going to cancel out, our kelvins are going to cancel out, and our joules are going to take care of our kilograms. So I'll show you that in a second. When we plug all these numbers in, we're going to end up with 738 meters per second. So think about that. These gases, these neon molecules, they should really be neon atoms. Neon gas particles, we'll call them, can travel at a speed of 738 meters per second. So that is super, super fast. All right. So now I'll show you what I did with the units, just so you know. So joules are equal to kilograms, meters squared, seconds squared. So we canceled everything else out but our kilograms on the bottom. So I'll show you that. So kilograms cancel out, and we end up with meters squared, seconds squared. But our calculation was all under a square root, so our final units were meters per second, which is what we were looking for. All molecules in a gas sample have the same speed, so that's why we keep talking about averages and not speed in particular or energy in particular. So just like people or cars, the collection of gas molecules exhibits many possible speeds. I'm not very fast, and I know Usain Bolt is very fast. So we are both people, but we don't move at the same speed, just like gas molecules. So the distribution of the speeds of these gas molecules is called a Boltzmann distribution, and it looks like this. Each point in a Boltzmann distribution gives the number of gas molecules moving at that particular speed. So say this was 1 through 100 gas molecules. If I pick this point right here, I'd say that's about 20 gas molecules moving at 200 meters per second. That's what that means. Every point gives the number of gas molecules moving at that speed. The peak indicates the most probable speed. So that's a little over 400, and that's close to our like 90 mark. So 90 of the particles are moving at that speed compared to the 20 at this slower speed. So this is the most probable speed at that temperature. But because we aren't catching gas molecules and seeing how fast they move individually, I'm saying that most of the molecules are moving at that speed, because this is just one point on the graph, and all these other points on the graph have almost the same number of molecules moving at that speed. So you can clearly tell that all of these molecules moving at these speeds add up to more molecules moving at these other speeds than this speed in particular. It also is not usually the average speed, as you see on this graph here. Average speed is a little bit faster than the mean probable speed, and that comes from the shape of the graph. So if you look at this graph, it's not perfectly symmetric about that peak, which means it's not a normal distribution if you've taken any stats. So that means that the average is not going to be the peak. It's going to be slightly to the left or the right of the peak, depending on the shape. And I think in most cases, if not always, for gas molecules and for Boltzmann distributions, the average speed is going to be higher than the most probable speed. All right. So let's look at some examples. So these are all at the same temperature. these are 4 different gases. So oxygen gas, nitrogen gas, water, vapor, and helium gas. And the area under the curve represents the total number of molecules in the sample. So just like I was showing you at the top, if that's 90 molecules and this is 20 and this is 30 and this is 70, then all of those numbers of molecules added together under this curve are going to add up to the total number of molecules in our sample. And if you've taken calculus, that should sound familiar to you. The area under the curve is equal to the sum of all of the possibilities. So this total number of molecules for this example is going to be the same for all 4 gases, which means that if we have the same number of molecules under this curve, that's why it has to be flatter, because it needs to take up more space to get the same number in this direction as this one had in this direction. And that's all that this paragraph is really saying. In the case of oxygen, the gas molecules have a small range of speeds and more molecules move at any particular speed. So the number of molecules is higher at a particular speed because oxygen has a smaller range of speeds. Helium has a wide range of speeds and it has fewer molecules at any speed. So there are fewer molecules moving at the most probable speed for helium than oxygen, but that most probable speed is higher. So that's the next thing we're going to talk about, is why these curves look different when they're all at the same temperature and they have the same energy. So notice the relationship between the Boltzmann distribution plots and the molar mass of the gases. Peak in the oxygen curve is farthest to the left, meaning it has the slowest moving molecules on average. The peak in the nitrogen curve is further to the right, which means that the nitrogen gas molecules are more likely to move faster than the oxygen molecules. So if we take a look at that again, so the peak for nitrogen is here, and the peak for oxygen is here. So the more likely amount of nitrogen molecules is going to be moving faster than the more likely amount of oxygen molecules. All right, and the helium curve is shifted furthest to the right, which means that they have very fast moving molecules, and it also has the smallest molar mass. So we see 32, 28, 18, and 4. So as our molar mass decreases, our speeds increase. Our speeds shift. Speed is higher. So average molecular speed depends on the kinetic energy and the mass of the particles. According to our molecular theory, if all gases have the same temperature and the same average kinetic energy at that temperature, that means that when there's a smaller mass, there has to be a larger velocity to balance out and get the same kinetic energy. So all of our smaller molecules, our helium molecules, which are only 4 grams per mole, are going to have a much higher velocity than our bigger molecules like oxygen, which has 32 grams per mole. That's going to move much slower. So slower velocity, higher mass. Smaller mass, higher velocity. So they are inversely related. So the curve for oxygen at a higher temperature, so now we're talking about the same molecules, same molar mass, now we're talking about a higher temperature. So at the higher temperature, the curve is shifted to the right. So the most likely speed is faster than the most likely speed at this other temperature. So at 25 degrees Celsius, the molecules are moving in it. Most molecules, or sorry, I should not say that. It's most likely that the molecules are moving at this 400 meters per second. At 1000 degrees Celsius, it's most likely that the molecules are moving at about 800 meters per second. So the O2 molecules move faster on average at a higher temperature so as the temperature increases, kinetic energy increases. And like I said, the mass is the same. So for kinetic energy to still increase, what is equal to mass velocity? Velocity has to change. So kinetic energy goes up, velocity must have gone up. So more molecules are moving at these higher speeds at a higher temperature. There were pretty much no molecules moving above 1200 meters per second at 25 degrees Celsius, and there's a whole bunch over here at 1000 degrees Celsius. So you guys should get very familiar with Boltzmann distributions. They tell you a whole bunch of information. They tell you about temperature. If the problem says that the temperatures are different, then the ones that are shifted most to the right are the highest temperature. If it says that the temperatures are all the same, the ones that are shifted most to the right have the smallest mass. So I'll write that here. Highest temperature, smallest mass on this side. Lowest temperature, biggest mass if the peak is closer to this side. So it's all about that peak. Right. So our summary of what we learned from Boltzmann distributions. Gases move with a range of speeds, so they have all those different speeds possible, not just one. And gases move faster. Temperature goes up, velocity goes up. Heavier gases move more slowly on average than lighter gases, so mass goes up, velocity goes down, because we have to have the same kinetic energy at the same temperature. All right, so that's enough about Boltzmann distributions. Now we're going to talk about something called diffusion. So your MindTap text goes into this a little bit in more detail, telling you that these gases move at super high speeds, like the one we saw in our practice problem, the nitrogen gas. I think it was nitrogen. No, it was neon. The neon gas moved at 738 meters per second. So super fast. But the gases don't actually travel that quickly when they're dispersing through the air. And that is because of diffusion. Diffusion is related to the mixing of gases. When your gas molecules are moving in an air-filled room, they're colliding with all the gas molecules in the air. So the oxygen molecules in the air, the nitrogen molecule in the air, the carbon dioxide molecules in the air are all blocking the path of that gas molecule from spreading throughout the room. So it takes much more time for the gas to get from one place to another than if nothing was in its way. And this process of moving through other gases, mixing of gases, is called diffusion. So you see that after mixing, your orange particles are still not all on the other side of the room. They're still mixing in the middle with these blue molecules. And now we're going to talk about something related. So all of the equations that you learn today are going to be related to effusion, not diffusion. But you need to know a little bit about diffusion to learn about effusion. So effusion is the movement of gas molecules through a small opening into a vacuum. So this time they are not in, these molecules are not encountering other gas molecules, they're just encountering this wall. So that small opening where they get through is so that small opening where they get through is kind of related to when they're hitting other gas molecules. So, but it's easy, and we can write equations for effusion. So Graham's law of effusion, this guy Graham, he came up with this law stating that the rate of effusion of a gas is inversely related to the square root of its molar mass. So this relates back to where we learned that gases with higher molar masses, bigger gases, move more slowly. So he's saying that again with this proportion. Lighter gases move faster, they effuse more rapidly than heavier gases, which move slowly or effuse slowly. So one form of Graham's law can be used to find the molar mass of an unknown gas. And we do that by setting up this equation. The effusion rate of the unknown gas is compared to that of a gas with a known molar mass. So we know rate 1, we know rate 2, and we know M1. So we want to solve for M2. So you can measure the effusion rate of a gas even if you don't know what it is. And from that, you can find its molar mass. So let's do that for this problem. There's a sample of oxygen fusing through a small hole at a rate of 9 times 10 to the negative 6 moles per hour. So we know what that gas is, we know its molar mass, and its rate of effusion. The unknown gas, under the same conditions, effuses at this rate. So we want to find the molar mass of our unknown gas. So rate 1 over rate 2 is equal to the of molar mass 2 over molar mass 1. And we want to solve for molar mass 2, so I'm going to square both sides to get rid of that square root. So rate 1 over rate 2 squared is going to be equal to M2 over M1. These are molar masses. So if we want to get M2 by itself, we multiply both sides by M1 to cancel it out and put it over here. So now we have our equation solved for M2. Let's plug stuff in. So our rate 1 is our rate of oxygen, so 9.00 times 10 to the negative 6 moles per hour. And our 2 is the unknown gas, 7.93 times 10 to the negative 6 moles per hour. We're going to square that and multiply it by the molar mass of oxygen. So it's oxygen gas, so it's O2. So that's 32 grams per mole. These units are going to cancel out, and our units of molar mass for the unknown are going to be grams per mole, which is what we want. So when you plug those numbers into your calculator, you'll find that your unknown gas has a molar mass of 41.2 grams per mole. All right, so that is effusion.